The biggest, the fastest, the strongest, the most destructive. Even after the world witnessed the devastation wrought by atomic weaponry during World War II, we inexplicably built them bigger, bolder, and more deadly. On October the 30th, 1961, a Tupolev Tu-95V bomber opens its doors and drops its 27-ton load over Novaya Zemlya Island in the Soviet Arctic Ocean. The immense bomb descends almost gracefully beneath parachutes, allowing its plane to speed away as fast as its propellers will take it. Which is just as well, for when this Tsar Bomba, or King of Bombs, detonates, it produces the largest man-made blast the world has ever seen. The thermonuclear weapon explodes with a force of 50 megatons of TNT, more than 3,800 times stronger than the bomb dropped on Hiroshima. Its mushroom cloud reaches 60 kilometers in height, and the flash of the detonation could be seen 1,000 kilometers away. The heat from the explosion is enough to cause third-degree burns at a distance of 100 kilometers. The colossal destructive force of the Tsar Bomba explosion was hard to fathom. But earlier that year, astronomers had witnessed an explosion that was some 10 billion times stronger. In a spiral galaxy 45 million light-years away from our own, a giant star reached the end of its life in spectacular fashion. As fusion came to a halt in its core, the repulsion of its electrons could no longer resist the crushing force of gravity, and it collapsed in on itself at nearly a quarter of the speed of light. The sudden implosion sends temperatures soaring and results in a supernova explosion that spews stellar material over many light-years. But if supernova explosions are more powerful than anything we can conceive of on Earth, hypernovas put even them to shame. These rare, super-powerful stellar explosions result from the death of stars more than 30 times more massive than our Sun. A black hole is created in the center, and scorching winds of newly forged nickel and jets of radiation plow through and ignite what was left of the star. Hypernovae can be 10 to 100 times brighter and more powerful than a supernova. They are believed to be the most powerful single event in our observable universe. And all of this destructive force results, ultimately, from the pull of gravity on the atoms that make up these dying stars. So, you could be forgiven for thinking of gravity as vastly powerful. Indeed, every moment of our lives is shaped and defined by gravity. From the convenience of remaining stuck to the surface of the Earth, to the mental calculations we make when playing sports, even to the immense challenge of engineering rockets to escape our planet's inexorable pull. But gravity is just one of 4 fundamental forces that control our universe. The strong nuclear force holds our atoms together. The electromagnetic force permeates all of space and delivers the radiation which lights and warms the cosmos. Even the weak nuclear force has a vital purpose, driving the nuclear fusion in the hearts of stars. Indeed, when compared to these other heavy hitters, the force of gravity pales in comparison. The strong force is, fittingly, the strongest force known to nature, followed by the electromagnetic force and then, unsurprisingly, the weak force. And at the bottom of the scale, gravity, by some distance. It is weaker even than the so-called weak force. To be exact, by 10 to the 25th power, or 10 trillion times. In order for us to feel the effects of gravity, we must work on cosmological scales, with entire stars and planets' worth of accumulated matter. In simple terms, the stored chemical energy in the legs of an ant can overcome the gravity of an entire world. Gravity's relative weakness has baffled scientists for years and has come to be known as the hierarchy problem. And this mystery may be linked to another cosmological puzzle. Where does this omnipresent but practically powerless force originate? To answer these century-old questions, we will have to take a trip billions of years back in time, billions of light years away in space, and possibly even to another dimension. This video is sponsored by CuriosityStream, the documentary subscription service. Question: how big was the largest black hole ever discovered? A. 1 billion times the size of our Sun. B. Roughly the size of the Milky Way. C. Very big. Or D. Not very big. TON 618 is 66 billion solar masses, similar in size to the entire Milky Way. And so, my recommendation from CuriosityStream this month is the fascinating Zenith, Advances in Space Exploration, a new 13-part series exploring just how humanity will be able to journey to the stars. And for this and more, CuriosityStream is a bargain at less than $20 a year, with a wide range of documentaries on topics ranging from science to music, nature to sports, with new shows popping up every week. So go to curiositystream.com/History of the Universe to sign up, and using the promo code History of the Universe will save you 25%. Gravity was the first force to be recognized by scientists, and yet, to this day, remains the most shrouded in mystery. Isaac Newton may have been a brilliant mathematician, but he was, by all accounts, a dour and serious man. With no time or interest for the opposite sex, or indeed any sex at all, he remained a virgin all his life, and what joy he experienced was scarcely visible on his face. Legend has it he only laughed in public twice. But of course, it was under this ultimate focus, distracted by neither jollity or intimacy, that Newton was able to formulate his famous theory of universal gravitation. In 1666, a deadly outbreak of plague forced Cambridge University to close, and Newton returned to his family home, Woolsthorpe Manor in Lincolnshire. Here, in an isolation much like that experienced by many of us in the last 2 years, Newton found himself uniquely inspired. He continued to experiment with light and optics, and took long walks around the grounds where, it is said, he witnessed something that would come to define physics. Whether or not this is myth, it was a myth perpetuated by Newton himself. After dinner, the weather being warm, we went into the garden and drank tea under the shade of some apple trees. He told me he was just in the same situation as when, formerly, the notion of gravitation came into his mind. It was occasioned by the fall of an apple as he sat in contemplative mood. Why should that apple always descend perpendicularly to the ground? Thought he to himself. Letting his mind wander above the branches of the apple tree, he further considered this attractive force extending beyond the atmosphere of the Earth. In that moment, he didn't understand gravity in its entirety, but as the apple struck the ground, it sowed the seeds of his pivotal theory. That theory, simply, is that all masses experience an attractive force pulling them together. The strength of that force is proportional to their respective masses, and inversely proportional to the distance between them. Early 18th century scholars applying Newton's theory of universal gravitation found that it worked remarkably well to explain the motions of the planets, moons, and stars. But Newton, in characteristically dour and pessimistic fashion, was still not satisfied. That gravity should be innate, inherent, and essential to matter, or that one body may act upon another at a distance, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Gravity must be caused by an agent, acting constantly according to certain laws. But whether this agent be material or immaterial, I have left to the consideration of my readers. In other words, the maths is correct, but he has no idea why. But while this mysterious agent remained undiscovered, Newton's theory persisted for some 200 years. Over that time, more precise astronomical observations gradually revealed phenomena that the so-called universal gravitation was unable to explain. The orbit of Mercury, for instance, didn't conform to the mathematical dance predicted by Newton's theory. And the equations also came short of explaining how light, with no measurable mass of its own, could be bent and deflected by other objects. Newton's self-skepticism was justified and ahead of its time. The gravity of the situation became increasingly apparent to early 20th century astronomers as more and more advanced telescopes and instruments began to probe the cosmos on scales never before imagined. Time and time again, Newton's theory fell short, and it became clear that a more nuanced mathematical explanation for gravity would be necessary. And so, in 1913, an alternative theory was proposed, but not by the man you may imagine. Gunnar Nordström was a Finnish physicist hugely inspired by a certain German's recent theories of special relativity, in which space and time themselves are redefined as phenomena intrinsically tied to frames of reference. Nordström seized upon and solved the equations set by the German and went on to expand his own theories to consider how this might apply to gravitational attractions. In them, he posited a notion that must have seemed outrageous, as it was difficult to grasp. What if, Nordström suggested, space and time were not flat, but instead curved? Such a bizarre dimensional geometry would be enough to explain gravitation just as well as Newton's theory, even better in some circumstances. Unfortunately, although Nordström's mathematics were internally consistent, they couldn't be confirmed by experiment or observation. A solar eclipse in 1919 revealed bending of light that didn't fit with his theory's predictions. Nordström's ideas were dead in the water, but the seed of curved spacetime had already been sown. The very German physicist whose equations first guided the Finn now seized upon his revolutionary ideas and made them his own. 2 years after Nordström, the German, Albert Einstein, published his own theory of general relativity, with curved spacetime central to all observable features of gravity. But far from being resentful, Nordström nominated his friend and colleague for the Nobel Prize. Twice. Einstein himself found it helpful to think about the knotty questions surrounding the nature of gravity with his Gedanken experiments. He created an entire laboratory of thought experiments. In one, notionally inspired by seeing a painter fall from a roof opposite the patent building where he worked, he imagines a man falling from an impossibly tall building. As he falls, untroubled by fear of any imminent impact, he may consider whether he is, in fact, falling at all. If he releases any object he was holding, it would remain in the same position beside him. He would be forgiven for thinking that there was no gravitational field at all, that he was floating, weightless, and at rest in space. Such a comparison serves to demonstrate that our perception of gravity is strongly dependent on our frame of reference. Only by looking at the windows of the building scrolling past would our luckless man be aware of his imminent fate. Another of Einstein's thought experiments places our unfortunate falling man inside a large closed box, that is, this time floating freely in space. He would be truly weightless within it. That box then has a rope attached to a surface that was to become its roof, and that rope is pulled on by some divine and omnipotent being with a constant force. The box would be accelerated uniformly upwards, and the man inside would drop to the floor. All his senses would tell him that he now has weight. He is indeed sitting on the floor of the box as he would if the box were sitting on the surface of a planet, like Earth. He could be forgiven for thinking that he was in a uniform gravitational field, when in reality no such field exists. This example serves to demonstrate that the effects of gravitational acceleration are indistinguishable from those of a more traditional force-induced acceleration, the likes of which we experience in a speeding car or a cornering roller coaster. This so-called equivalence may seem obvious to us, but it became an important facet of Einstein's theory of general relativity. Although physicists are still looking for ways to experimentally verify this equivalence and other assumptions that underpin general relativity, the advanced theory, first proposed in 1915, still holds up to detailed examination. General relativity relates matter's energy and momentum to the curvature of space-time, which in turn dictates how everything embedded within it, both material and intangible, behaves. Importantly, the theory is able to explain the strange wobble in Mercury's orbit, since the tiny planet passes so close to the massive Sun that it receives an extra relativistic push. And general relativity also satisfactorily explains the curvature of massless light. All of our perceived reality resides within the 4 dimensions of spacetime and is a slave to the geometry of that fabric. If spacetime is curved by massive objects, then light has no choice but to curve as well. Today we have tested general relativity time and time again, and it does appear to hold true. But while Einstein's theories broke ground in describing how gravity works on cosmological scales, they do little to reveal the true nature and origin of this mysterious force. In other words, echoing Newton's statement 250 years earlier, the maths checks out, but we still don't know why. Physicists have spent the last 100 years searching for gravity's beginnings, in the hope that it will shed light on its true nature, why it is ultimately so weak, and even how the universe around it came into existence. One billion years ago, on Earth, not a lot was happening. For roughly 800 million years, the planet has been stuck in a stagnant, stinking stasis. No major continental reshuffles, no waxing and waning ice ages, no fluctuations in oceanic or atmospheric chemistry. Life, which has made promising advances since its appearance, diversifying throughout the oceans, inventing photosynthesis, and even learning how to cooperate, now just seems to stop in its tracks. Evolution stalled, and for this unthinkably vast span of time, amounting to nearly a quarter of all of Earth's history, nothing very interesting happened at all. This period has been fittingly named the Boring Billion by geologists, and yet, in the Earth's distant southern skies, far beyond the Magellanic Clouds, an event is taking place that is by no means boring. Two black holes, each more than 30 times the mass of our own Sun, are locked in a fatal dance, spinning faster and faster around one another until eventually, catastrophically, they collide, merging to become one supersized body. Unfortunately for the Proterozoic Earth, this spectacular event is unable to punctuate the tedium, as not only are the black holes themselves non-luminous and therefore invisible, but they are also more than 1 billion light-years away. There's nothing for anyone or anything to see, hear, or feel for 1 billion years. Until, at 9:50 AM on the 14th of September 2015, a remarkable instrument comes online. 2 advanced laser interferometer gravity wave observatories, known as LIGO, had just been completed in Hanford, Washington, and in Livingston, Louisiana, and had been switched on just 2 days before. They were still in their test mode, with no formal research having begun, when researchers picked up an incredibly loud and clear signal. It was so perfect that nobody believed at first that it was real. They thought it was just another calibration signal designed to test the instrument's sensitivity and the researchers' analytical skills. But when no one owned up to devising such a drill, they were forced to conclude that their brand new detector had made its first detection. This was in itself remarkable. Throughout its proposal, funding, and construction, LIGO received more than its fair share of criticism. Indeed, the instrument had been conceived as a way to detect a phenomenon that had only ever existed as a theory. It was Einstein himself who posited the idea of gravitational waves radiating out through space-time from a sudden and massive gravitational disturbance. But space-time is our reality, so how could we possibly detect ripples within it without anything to compare it against? LIGO intended to search for these minute distortions using two lasers reflected back and forth between a sequence of mirrors, which then converge at a single point to cancel each other out. If a gravitational wave passed through, they would change the lengths of these laser beams, causing a mismatch that could be detected at the point of convergence. Critics doubted that the instrument would be sensitive enough to detect these faint ripples, or indeed, that they existed at all. So it's little wonder that scientists were surprised by their discovery in 2015. The signal they detected was short, lasting just a fifth of a second, but corresponded to a vibration that was in the range of human hearing. And the source of this chirp? The cataclysmic collision of two black holes more than 1 billion years ago. The merger had released nearly a quindecillion joules of energy, that's 10 to the 48th power, as gravitational waves radiated out in all directions, travelling at light speed for 1 billion years, until they finally reached LIGO just 2 days after it came online. And since that first remarkable detection, scientists have heard countless more chirps and beeps from gravitational waves rippling through the fabric of the cosmos. Their success was confirmed beyond a doubt in 2017 when a detection of gravitational waves coincided with a burst of gamma rays, and then observational evidence of a bright new star. The source this time was not merging black holes, but merging neutron stars. LIGO's critics were firmly silenced, as the researchers were awarded the 2017 Nobel Prize in Physics for their definitive detection of gravitational waves, and further confirmation of Einstein's general relativity. But what does this cutting-edge science tell us about the nature of gravity in the cosmos? The existence of gravitational waves implies that gravity is not simply a force between individual objects, but a field that extends throughout all space and time. Ripples move through that field at the speed of light, not instantaneously as Newton's original formulations implied. That means that if the Sun were to suddenly blink out of existence, the Earth would continue orbiting the space it had inhabited for a full 8 minutes, unaware that anything had changed, before the change in gravitational distortion caught up. Disconcerting though this may seem, for physicists it is a comforting conclusion. The other fundamental forces are also manifest as fields, with energy being transmitted through them as waves. Light and heat are just ripples in the pervasive electromagnetic field of the cosmos, and are too limited to a maximum speed. So we would be ignorant to the disappearance of the Sun's light too for a full 8 minutes. Gravity therefore behaves similarly to the other forces, and it's not unreasonable to think that its origin can be tied to them as well. And it is in the pursuit of this mystery that LIGO scientists hope gravitational waves can provide another clue. Today, we detect space-time ripples all the time from things like black holes, neutron stars, and supernovae. But theoretically, there should be another wave lurking in the background, behind all the noise of the lives and deaths of stars. Astronomers believe that there should be faint gravitational ripples pervading the universe, which have been travelling the vast cosmic ocean since its birth. Currently accepted models for the universe's earliest moments see the newborn cosmos suddenly and almost instantaneously expand, inflating to many uncountable trillions times its original size in less than 1/1000th of a billionth of a billionth of a second. Whatever heat and energy that had existed in the universe before inflation was now spread unimaginably thinly, leaving space cold and empty. Yet, of course, that is not how the cosmos is today, so cosmologists imagine a period of reheating that immediately followed. They hypothesized that whatever force, field, or particle that was responsible for inflation in the first place decayed away and transformed into energy and particles to fill the new universe. This is considered by some to be the real Big Bang, since this is the event that filled the cosmos with everything needed to make our universe as we know it. And theory suggests that this reheating event would have released energy in the form of gravitational waves, which would have spent the last 13.8 billion years traveling through the fabric of space-time. They would be faint, but these primordial echoes, if our theories are correct, are washing over us right now. Unfortunately, the groundbreaking LIGO instruments in Washington and Louisiana may be able to pick up a black hole merger a billion light-years away, but they are not sensitive enough to probe the beginning of the universe. New instruments are being developed right now, including the European Space Agency's Laser Interferometer Space Antenna, or LISA, which, it is hoped, will have the resolution to filter out the clamour from the stars to see the swell of space-time itself. The types of waves these new instruments detect also offer a chance for us to better understand the process and end of inflation. It is a period of time we will never be able to probe with traditional astronomy, since the universe was no more than an opaque plasma until it was around 380,000 years old, and inflation occurred less than a second after the true Big Bang. We don't know if reheating was slow or rapid, but the pattern of gravitational waves from each scenario would be sufficiently different to allow us to reconstruct this remarkable event. The detection of primordial gravitational waves from the end of inflation would also confirm another assumption, that the gravitational field itself is intrinsic to the universe as we know it. While it may seem obvious and reinforced by gravity's similarity to the other four fundamental forces, it is an important experimental result that provides boundaries on what is and isn't likely during this improbable period in the history of the universe. Today, the shape of space-time is warped by the presence of massive objects. Does the gravitational field require mass in order to manifest? Results from the Large Hadron Collider in 2012 verified that the mass of normal matter is derived from the Higgs field and its corresponding messenger particle, the Higgs boson. But modelling suggests that the Higgs field didn't come into existence until long after the end of inflation. So is this the origin of the gravitational field as well? While the link between mass and gravity in the modern universe is indisputable, they are in fact separate and mutually exclusive phenomena. The Einsteinian notion of gravity is in fact created by a combination of energy and momentum, not explicitly mass. This much is apparent by gravity's effect on the massless photons that make up light. And so, gravity doesn't need the Higgs field to work. Its origin can long predate the origin of mass in the cosmos, although its effects become unrecognizable in a universe where matter and mass are not yet related. And so, the general consensus among early universe cosmologists is that gravity emerged during the bizarre and incomprehensible Planck epoch, when the universe was just a Planck length in size, around 100 billion billionth the size of a proton. But the nature of that gravity would be very different to that in the modern cosmos. Efforts to probe the behavior of gravitational spacetime on such small scales have yielded troubling and unsatisfactory answers. But new ideas are gaining ground, which offer to transform our understanding again, just as Einstein's revelations and LIGO's discoveries have done before. These theories are as mind-boggling as any in the pre-inflationary universe, but they offer to resolve the long-standing and as yet unresolved question of why gravity is so mysterious and so weak. Lisa Randall is filled with confidence and adrenaline as she chalks her hands and flexes her fingers, ready for the climb ahead of her. Stepping back to check her planned route for the final time, she sees chalk on handholds favoured by previous climbers, and pins and hooks ready for securing ropes at stages along the vertical rock face. She isn't nervous. Just the day before, she had scaled Yosemite's famous Half Dome and is feeling comfortable in her climbing prime. Happy and confident, she steps up to the rock, eases her toes into a crack, and begins her ascent. Randall is no stranger to gravity and to its weakness in comparison with the other fundamental forces. By 2003, she had made a name for herself as an instinctive and especially talented theoretical physicist, with some seemingly outlandish but potentially inspired theories on the nature of reality. But right now, her thoughts are not of her theories, or of the upcoming conference in which hundreds of like-minded physicists will discuss her work, but rather the rock that is mere inches from her nose, and the rough surface of the stone beneath her fingers. Gravity is so weak that here in Yosemite, as with everywhere on Earth, the tension in a single rope is enough to overcome it and hold a human body when fingers slip. Unfortunately for Lisa Randall, she is near the top of the first leg of her climb and is yet to secure a rope to the first anchor point, just a few feet above. And it is here her hold fails, and gravity takes over. For all its weakness, when there is nothing to stand in its way, it speeds Randall back to her starting point, accelerating her by 22 miles an hour for every second of her fall. One of the major barriers to understanding gravity in the way that we do the other forces is the fundamental incompatibility of the two leading theories in physics. General relativity, as defined by Einstein, describes the large-scale behavior and interaction of objects within a curved spacetime. But at the other end of the physics spectrum, quantum mechanics has been adopted to explain behaviors on the smallest possible scales. Almost all large-scale phenomena have been broken down into their smallest constituent parts, the fundamental particles or virtual particles that represent the quantized universe. Thus, the electromagnetic field that permeates all of space has been quantized into individual packets, or particles, known as photons. The other forces likewise have virtual quantum particles, in the shape of gluons and W and Z bosons, that communicate their action across various scales. Even the fundamental particles of matter have been recognized as quantum manifestations of a pervasive energy field. But gravity is the exception to the rule. A quantum messenger particle for the gravitational field has been theorized and even given a name, the graviton, but it has never been detected. Some doubt that it ever could be detected. If the gravitational field is woven into space-time, then isolating the quantum packet of that field would be nigh on impossible, tantamount to reducing our reality to the 4D pixels that make it up. Such pixels would of course only appear when viewed from outside the fabric itself, something which we are simply unable to do. And if it were possible, the energies required to resolve a graviton in a particle accelerator would require an instrument with a diameter larger than our solar system. And on top of this, traditionally mathematically supported theories of gravity begin to break down at the smallest scales of quarks and leptons. General relativity suggests that any source of energy or momentum should distort spacetime. This means when you attempt to quantize spacetime to the smallest degree, then gravity itself becomes an excitation, a source of energy. That energy is enough to distort spacetime, to create more gravity, which creates more excitations, more energy, more gravity, more excitation, and so on. Unresolvable infinities are bad news for any theory. This self-excitation, like the uncontrollable fishtailing of a trailer at high speed, is actually not uncommon in quantum theory, but physicists have found a way to mathematically constrain and correct for the so-called self-energy. But when it comes to quantizing gravity and spacetime, there are no simple measurements that can be made to rein in the self-excitation. Physicists describe gravity as non-renormalizable, which essentially means that space, time, and gravity cannot behave in the way we expect at scales smaller than the Planck scale. Gravity and the quantum world remain irrevocably at odds. Scientists have suggested alternate theories for the earliest gravity that existed during the Planck epoch. Loop quantum gravity is a scheme that conveniently avoids the need to renormalize quantum gravitational measurements by considering gravity in a purely geometric sense, rather than as a force. In it, space and time are constructed from closed loops that are woven into an extremely fine network, transforming the fabric of space-time from mere metaphor to reality. String theory provides an alternative but no less mind-melting approach. In it, reality is composed of tiny vibrating strings that exist over more dimensions than we can possibly ever experience. It suggests that the 3 dimensions of space and one of time are merely emergent properties of a bigger reality. And so, it is here we return to Yosemite. Lisa Randall wakes as she is airlifted from the site of her decisive defeat in the battle against gravity. Her head swimming, she sees not stars, but strings. But as her consciousness trickles back, the tantalizing glimpse of multiple dimensions granted to her by concussive imagination is replaced with disappointing lucidity. She is back in the limited, 3-dimensional world of the living. For the next few months, under enforced bed rest, she finally has time to finish her book and to try to explain her bizarre, multi-dimensional theories in a way that everyone can understand. Scholars of string theory generally assume that the other 7 dimensions necessary for the theory to work aren't visible to us because they are curled up to an imperceivably tiny scale. But Randall went so far as to suggest that these extra dimensions could be infinite in extent, provided space had a warped geometry. Taking Nordstrom and Einstein's concepts of curved space-time to another level, Randall suggests that our entire universe inhabits a 3-dimensional pocket of higher dimensional space. These pockets are known as branes, from the concept of membranes. Just like a pearl on a string can move side to side and experience only one linear dimension in our 3-dimensional universe, so our entire universe may be limited to 3 dimensions, even though many more exist beyond our reach. And Randall invokes these branes as an elegant explanation for gravity's elusiveness and its weakness. She suggests that gravity is not a fundamental property of the brane we inhabit, but that it is concentrated in another brane altogether. This helps to resolve the unanswered question of why gravity is so weak and is indeed so much weaker than it should be. Indeed, mathematical calculations from first principles suggest that gravity should in fact be 10 million billion times as strong as it is. The fact that it is not has been explained by another theoretical scheme known as supersymmetry, in which every particle has a supersymmetric sparticle that helps to shield it from some of the effects of the ambient universe. But following this theory through to its natural conclusion, that many sparticles throughout the cosmos would produce reactions that are simply not observed. So Lisa Randall and her colleague Raman Sundram found a way to keep the maths and explain what we actually see, by effectively quarantining some parts of the theory in another universe. And so, placing gravity on another 4-dimensional brane which is separated from our own by a short distance in a 5-dimensional bulk helps to resolve the contradictions inherent in supersymmetry. In this scheme, the effects of gravity decrease exponentially the further we are from the so-called gravibrane. Thus, in our reality, we experience only those gravitational effects that leak through from the dimensions where gravity is king. Our lack of success in detecting gravitons thus far may be a symptom not of their diminutiveness, but rather the very small quantum probability that they will stray from their own brane into our universe. Lisa Randall's ideas are tantalizing ones, and supersymmetry, string theory, and the multiverse are concepts that are rapidly gaining ground within the physics community. But it is hard to set such store by mathematics alone. Just as curved space-time seemed unfathomably complex to Nordstrom and Einstein's predecessors, so these new theories skirt the worryingly incomprehensible. And just as gravitational waves were criticized until the moment of their discovery, many scientists won't take these concepts seriously until there is definitive proof, if definitive proof is even possible. With hundreds of physicists, astronomers, and mathematicians now working on the problem all over the world, we will just have to wait to finally unravel the true nature of gravity and reality itself. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.